Hey everybody. So this is the kind of final concept. This would be question six. I don't even know what page we're on. This is question six in the final concept of this unit, where we generate electricity from magnetism and motion. All right. This gets at the idea though of flux, which we'll get to in a little bit. But the whole point here is that we're creating electricity. We're making a voltage, creating a voltage and thus a current. Current's what you see, right? Light comes on or you see the electrons move, but really what's happening with that magnet is it's creating a potential across it. And if it's got a complete circuit, then that current will flow. But it's really cool because you're taking this motion, this kinetic energy, and we're creating electrical energy. There's no batteries here. And so a lot of times the question will say, what could you do to increase the current produced? And they'll say increase the voltage or get a bigger battery. Well, that's not what this is. This is where we are increasing the voltage, yes, but we're doing it with a magnet, coil, and motion or flux between those two things, the magnetic field and the coil, creating a change in flux between them, and that produces an electromotive force, EMF, or induced voltage. Those are all the same thing. Anyway, let's jump into the questions here. So electromagnetic induction. This is Michael Faraday's big stuff. Actually, he did a lot of big stuff. So here's the picture at right. I've got a magnet, some coils, and the voltmeter here. Magnets move through the solenoid, inducing a current in the coil. I see the north is going in there. The voltmeter attached can read voltage. Where does the electrical energy come from? So where is that energy coming from? As I mentioned before, the magnet has no potential energy. That's not it. Kinetic energy of motion. The kinetic energy is becoming electrical energy. Kinetic to electrical is induction or is a generator. If we go the other way, that would be a motor, but that's this. Magnet is pulled quickly to the left. So the magnet is moving quickly to the left, right? Inducing a current. So that north is moving away and that induces a current. If you move it more slowly and then to the right, so then we're going back to the right here, right? How will it change? So we're going slower and opposite direction, okay? It will produce less current. Slowly means less. And then since it was going left, now it's going right, it'll go in the opposite direction. So it is that first one there. Less current because it's going slow, and right because opposite because it's a different direction that it was pulled before. And that will produce a different current. And that's that alternating current thing. All right, when the North Pole moves slow, now here we go. All right, North Pole, north, moves slowly toward the coil. All right, so look at the picture here. Actually, here, let's make that blue. North, slowly toward. So we're going towards it here. Blue. It induces a positive charge, small positive. All right. What happens to the magnitude direction of the current in the following cases? So we're going to go through and change those different things there and see how each one affects it. I'll go back to black. All right. North pole moves towards the coil, so it's the same direction towards the coil faster. So faster is the only thing changing. So towards the coil, towards would be same direction. Faster means more current. So faster means more current. And towards is the same direction. All right. Now we move away. So that's going to go in the opposite direction. And it's moving slower. So that means less current. I'll underline that too, since it's kind of underlining there. All right. North magnet is stationary, not moving. Well, it's not moving. You don't have a change in flux. You don't have the motion needed to create that changing flux, so there is no current. All right, and then finally, if I take a south pole, so we just switched to a south pole now, and towards, like the North Pole was moving toward before. Well, that south pole is going to make opposite direction, and toward the coil at the same speed will make the same current. Doesn't matter if it's north or south, it'll be the same current there. All right, south pole again, moves away. So south is opposite away. That double negative there, that double will produce the same direction, and it's faster, so it will be more current there. So, a lot going on there. Oh man, there's another one. The coil, now we're moving the coil towards a stationary magnet at the same speed that the magnet was moving toward the coil. Okay, so I think we're missing one key thing is what's the orientation of that magnet? I'll address that. So in just a second. So let's hit up the moving toward the coil initially. So it's moving the same speed. That's going to be the same current. It doesn't matter which one's moving. Now, I think we need to say the same orientation towards a stationary magnet, same orientation. So if we look up at that picture, we can see it's a north pole. So instead of the north pole moving toward it, now the coil's moving towards the north, and that will produce a current in the same direction. So now, even though the coil's moving the opposite direction as the magnet was, the relative motion between them, the north and the coil, are getting closer together, and it produces that same there. All right, lot there. All right, if I wanted to induce a largest possible, I can do 4 different things. All right, I can change the area, right? I can make more area. Now I do that through 3 things. I can change the number of coils, increase number of coils. So increasing the number of coils increases the area, and I can increase the size of each coil. Both of those will increase the area, right? I can increase the B magnetic field, right? Again, this is all getting at the idea that EMF is equal to change in flux, which is BA over time. So it's moving. So I can increase B. And finally, that actual speed or velocity, I can increase the speed. Right? So I could do 1, 2, 3, or 4. All of those are part of the equation for increasing it. And that is the first part of induction.